Welcome everyone to the second video talking about statistics, where we'll review what we talked about last semester, Boltzmann Statistics, okay, and the Boltzmann distribution function. Okay, so just kind of quick video here reviewing these things we talked about last semester, right? But basically, right, what is Boltzmann Statistics? Okay, and the idea is, let's suppose we have some container of n molecules, right, that can occupy different energy levels. Okay, and the energy levels kind of shown here. Right, and then each way we occupy those energy levels gives us a different configuration. That configuration has a different energy, right? There's a variety of different energies, variety of different energy levels we can occupy, right? And we use some approximations that the energy is just the sum of the energies of each particle in my system, okay? And that there's no weighting between the different energy levels, right? Each energy level is likely to be occupied, assuming you have infinite energy, right? So given that, we can calculate this weight function that was related with the probability of being in a given energy level and having a given set of configurations, okay? And when we do that, okay, we can then get out by the Boltzmann distribution function by solving for what is the optimal energy level, kind of that minimum energy. And again, we get that by taking the derivative of this weight function that's related to the probability, and then divide that by or should I take the derivative and setting a equal to 0 and solving that equation, okay? Right, and so when we do that, we can have a couple of constraints that the energy must be conserved and the number of particles must be conserved, right? So when you do that, right, you get back this Boltzmann distribution function, okay, which is given here, right? The probability of being at some energy level, okay, is given by this equation here, e to the minus beta epsilon I, divided by the sum over e to the minus beta epsilon j, okay? Where q here's that partition function we talked often about last semester, okay? And then beta, right, is just 1 over kt, k being the Boltzmann's constant, okay? And so, right, that gives us our probability distribution function, okay? And then we can use this, right, this Boltzmann distribution function, okay, and ask different things about what is the relative population between two energy levels. We can kind of use this formula and such, right? And this is another type of distribution function, a probability distribution function, right? And so this will be relevant when we talk about spectroscopy, okay? Because so when we talk about quantum mechanics, we talk about kind of energy levels of vibrational states and rotational states and electronic states and things like that, right? And your kinetic energy, and we'll solve for all these different things, okay, for your atoms and molecules, right? And then once we have that, right, once we have these energy levels, we can ask things about, like, I have a collection of n molecules at room temperature, right? What is the occupation of these different energy levels? And those occupations is given by these Boltzmann statistics, okay? And then that's relevant to spectroscopy, okay? Because if I want to take a spectra of some molecule, right, the molecule is absorbing energy at some level, okay? And then it absorbs that energy and creates an excited state, right? But it's going from some initial state to some excited state, right? Well, I need to know what my initial state is, okay? Is my initial state just the lowest energy state for all molecules, or are some molecules at a higher energy state and some at a lower energy state? And what we'll see with vibrational, especially rotational spectroscopy, that these Boltzmann statistics play a key role in the shape of what the spectra looks like, okay? Because relative occupations is related within the relative heights of your peaks in your spectra, and so the shape of a rotational spectra is very much determined by these Boltzmann statistics, these energy levels and the spacings between them. And we'll get a lot more into that detail when we talk about kind of spectroscopy and quantum mechanics, okay?